Hey guys, hopefully everybody got the link to join in. If not, you're viewing this afterwards. Let's give everybody about 1 minute to show up, and then we'll get going on this. I'm going to load up the chat for this. So give me just a minute. That way I can keep track of what everybody's saying. Nice, Jeremy. I just saw that you posted first. Okay. Hey, Jen. Hey, Tanya. Evening, Steven, Chantel, Rosa. So we got a good crowd here. There was a question about a 3x5 card. So yes, it is absolutely true that you can bring a 3x5 card to the final. You can write on one side of it. Can't write on both sides, but you can write anything you want. So anything you want to write on there, you're free to write on there. So everything's flipped for you guys still. Let me check and see what I can do on this end. Let's see. Okay. Hold tight for 1 minute. Double checking to make sure I can flip the screen. This is one problem with the new operating system that I've got. My encoding software is having issues with my HD cam. It's trying to keep everything reversed. So I have to reverse all my settings from my old streaming software. Okay, is that working? Okay, good deal. All right, so I can actually see it in reverse, but you guys are seeing it in the right direction, so it's going to get me a little bit backwards. All right, so we're going to work our way through this. We have got a number of topics to cover tonight. See what we can get through. All right, we're going to start with stoichiometry. I'm going to give you guys a quick tour of what I'm planning to cover. I'm going to cover stoichiometry. I'm going to cover conversions. I'm going to cover molecular naming and formulas, ionic naming and formulas, reaction types, functional groups, organic naming, skeletal structural and condensed structural formulas, and cis versus trans structures. So we're going to get through as much as we can in the next hour. So let's see what we can cover. As always, I want you guys to stop and ask questions when you get them. And let's get started. Okay. Stoichiometry is all about ratios. Let me flip over to different screen for 1 minute. Okay. So stoichiometry. If we were to put this into English, it's all about ratios or proportions. We had to have two things. We had to have moles. We had to have a balanced reaction. So the trick to this really was, if I didn't give you either of these pieces, you had to get to these pieces. So let's do just a typical problem. A reactant here. We've got a reactant here. We're going to make a product. And the question is, how much NH3 in moles could be made if 6 moles of H2 fully react? Okay, so here's our question. It's always about a have and a want. It says, how much NH3? Okay, well, I guess this over here That's going to be my want. It tells me that I have 6 moles of H2 that fully react. So this is going to be my have. So really, it's just like a conversion where I'm trying to take what I've got and I'm convert it to what I want. Before I do that, I just have to double check I've got moles, and I have to balance first. So we're going to balance both sides. We're just going to take one element at a time, and I'm going to start with n's because they look easier to me. If I put a 1 here, always start with low numbers. Keep it as simple as you can. So putting a 1 there, these multiply through. 1 times 2 gives me 2 n's. So then we bounce over to the other side of the net. If I want 2 n's here, I'll have to put a 2 there. 2 times 1 gives me my 2 n's. So now I've got 2 n's on each side. N's are balanced. Now I've got to balance my h's. So I'm going to leave this up to you guys. I've got h's here and h's here. What am I going to put in this blank to balance that reaction out? So take a minute. While you're doing that, I'm going to put a marshmallow in the cocoa. I don't know if you guys can tell, but my voice is starting to go away, so I'm hoping I last the hour. So go ahead and type in chat what number you think should fill in that blank. Okay, I'm getting 3s all around. That's a pretty solid answer. 3 is the number that's going to balance that out. So let's hop back into this. Just double checking that. Pop a 3 in. 3 times 2 gives me 6. 2 times 3 gives me 6. So 6 h's on each side. We're good to go. Okay. Moles, check. Balanced reaction, check. Good to do the stoichiometry. If you look at the problem, they only give me 1 number to start with. So that's a good place to start with the math problem. 6 moles of H2. Now, this is what I have to start with, and I want to cancel that out. So I'm going to put moles of H2 on the bottom because the opposite sides are going to cancel. I'm going to put moles of what I want on the top, and that was NH3 because the problem said how much NH3. So where are we going to get these numbers from for the conversion? We're going to go up to the reaction that we just balanced. That's why it's key that we balance this correctly. So for the H2, I'm going to put a 3. For the NH3, I'm going to put a 2. So we get these numbers that go into the ratio from the balanced coefficients. We only use the ones that we have to use. So I used H2's coefficient, and I used NH3's coefficient. And then we multiply across the top. We divide by what's in the bottom. So 6 times 2 divided by 3. That gives me 4 moles of NH3. Okay. Any questions on where any of these pieces came from? I'm going to give you guys just a minute before I move on. Okay. So no questions so far, so I'm going to go ahead and move on to the next topic. Now there are more problems that are related to stoichiometry. They do get harder. If you want to look up limiting reactant problems, if you're not as comfortable with the stoichiometry, I would look up limiting reactant problems. Because again, this is a survey review. I want to hit as much as we can. So we're going to hit topics broadly. Okay, conversions. I want to do 2 types. I want to do metric. And I also want to practice a grams to moles. And also, let's do a grams to molecules. So we're going to do 3 different conversions just for practice, but they all pretty much work the same way. So let's start with the metrics. This is a really good thing to put onto your note card. For example, there are 1,000 milligrams in a gram. There are 1,000 meters in a kilometer. When you looked at one of the first lectures we covered for my online folks, that's Module 1, we had a table of metric conversions. So put your metric conversions on the note cards. It'll help you on the final. Let's say that you had a sample problem that had you taking, let's do millimeters to meters. Okay, I've got 6,798 millimeters, and the problem says convert this many millimeters to meters. So straightforward enough problem, not a whole lot there, but it's a math problem. So we're going to take the only number it gives us, we're going to convert over to meters. 6,798 millimeters. And just like we did in the stoichiometry, I'm going to cancel out what I don't want. This is what I had already. This is what I want to end up with. So I'm going to cancel out what I have by putting millimeters on the bottom. I'm going to end with what I want by putting it on the top. And then the relationship, which you have to get from memory or from your note card, just being familiar with metrics, there's 1,000 millimeters for every 1 meter. So memorization or note card. Setting it up though, remember, opposite sides cancel, left us with the unit that we wanted. 6,798 times 1 over 1,000, 6.798 meters. Okay, so that was an example of a metric conversion like you might see on the final. Now, next topic, still in conversions, we're taking grams to moles or grams to molecules. This is something else that might be good to add on to your note card. It's a diagram, mass in grams going to moles, going to molecules, going to atoms. Now, if you want a full run through all the way through to atoms, if you take a look at our final exam review sheet with our topics and videos, you can make it all the way through to atoms. We're going to focus on the first 3 blocks because really they're the most practical, the ones that you're going to use the most. So we're going to try to convert, 22 grams of CO2 into moles and molecules. So we're going to do both. So let's start with that 22 grams of CO2. Okay, now I'm going to park that there for just a minute and go back to our diagram. Now we can flesh this out a little more by, on these arrows, writing out the conversion factor that we're going to need to go between mass and moles. We'll need the molar mass, and that we get from the periodic table, which you'll have a periodic table available during the exam. Moles to molecules, we're going to use Avogadro's number, which is 6.022 times 10 to the 23rd, and that's molecules per mole. And then the last one, going from molecules to atoms, would use the chemical formula. So for example, if we were looking at H2O, then this last one just says that there would be 2 H's for every H2O, or there would be 1 oxygen for every H2O. It's the ratio of the parts to the whole in the chemical formula. Okay, so let's look at our example. We've got 22 grams of CO2, so I'm starting in mass. I want to take this into moles. So we'll call this conversion A. We'll start there. We'll wrap up with conversion B, taking it into molecules. Picture yourself standing on this little block. I'm going from mass over to moles. So that's one hop. However many blocks you have to hop over, that's how many conversion factors you're going to need. Just like before, I'm going to try and arrange things so I can cancel out what I have to get what I want. When I'm done with this, I want moles of CO2. I want to cancel grams. I want to end in moles. So we need a relationship between moles and grams for CO2. If you look at the periodic table, C and O weighs about 16, C weighs about 12. It's CO2, so I've got one C, two O's, so that's 12 plus 2 times 16, that's 32. 12 and 32, 44 grams per mole. So let's go over here. I'm going to say for every 1 mole, I've got 44 grams. So same math as before, multiply across the top, divide by what's in the bottom. 22 over 44 is 0.5 moles of CO2. So then taking her the next step after that, we just answered the first part of the problem. The first part saying convert into moles. The second half wants us to take it all the way to molecules. We could continue with the answer that we have, but I want to show this to you guys from scratch. We're going to start again with 22 grams of CO2. Only this time, we're not just going to moles. We're going mass. We're hopping once to moles, twice to get over to molecules. So we're going to take this, and for every time we have to hop a block across, we're going to add in a conversion factor. So just like before, I want to cancel grams, get to moles. That gets me to here. To get to this block, I had to use the molar mass. So because we're still using CO2, it's still 1 mole, 44 grams. But now I don't want to end in moles. My goal in the second half is to end in molecules of CO2. So I've got to cancel moles. And I've got to end in, I'm going to write this on a diagonal just so I have room. I'm going to end in molecules. And for every 1 mole, just like saying 1 dozen is 12 eggs, 1 mole of CO2 is 6.022 times 10 to the 23rd molecules of CO2. So let's double check the way we have it set up. Grams canceled, moles canceled. I'm left with molecules. Now, I want you guys to try typing this into your calculator if you have it handy. 22 divided by 44, and you're going to multiply by 6.022 times 10 to the 23rd. And it doesn't matter the order. You could multiply 22 by Avogadro's number first, and then divide by 44, as long as you're doing the right operations. So take a minute. I want you guys to figure out what should go into this block. So find a final answer there. All right, let's try this now. All right, just let me know when you guys can hear me. We should have some sound going. And yeah, just stay on top of that. Just let me know. And okay, yeah, between when I hit the audio to turn it back on and when you guys hear it, it's about a 12-second delay. Okay, yeah, no worries. We'll get this done. Okay, ionic naming and molecular naming. So these two topics are pretty closely related. If we are, oh yeah, Tanya, I'll go back to the previous answer. All right, so conversions, just going back to the previous answer, we had 22 divided by 44. That works out to about a half, 0.5, just like we got before. 0.5 times Avogadro's number is 3.011 times 10 to the positive 23rd. Do you guys have any questions on that one before we move on? Okay, if you don't have any questions, I'm going to keep rolling with this. Okay, no problem. Okay, first step in either being able to recognize or write names and formulas for ionic or molecular compounds is being able to tell what kind of compound you have. You've got to have a distinction between the two because they each have their own rule set. Okay, let's say we're looking at NaCl versus NO2. If we were to look at a periodic table, and this is going to be very rough, but you'd see Na over here. You see Cl over here. You've got N over here and O over here. There's a stair step on the periodic table. Anything that's up here, these are the nonmetals. Over here, I've got the metals. If we're going to tell between between two different kinds of formulas, molecular and ionic, we have to be able to tell what kind of compound we've got. If I have the presence of a metal and or a polyatomic from your list of 10 polyatomic ions, something good to put onto your note card, then I'm going to have an ionic formula. Has its own set of rules. If I come over here, N and O are both nonmetals. If I have all nonmetals, that means I'm going to have something that's molecular. Now, if I have something that's molecular, that's where we had prefixes like mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And that stands for 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So we're going to need those prefixes to be able to name molecular compounds because molecular compounds are the only ones that use these. Something great to put onto your note card. Okay. Let's say that I've got CO, carbon monoxide. Carbon, also a nonmetal. Oxygen, a nonmetal, just because of where they show up on the periodic table. So this is molecular. Now, the only time we can ever leave off a prefix is when there is one of the first element that we're going to name. So we wouldn't call this monocarbon. We're just going to say carbon. and you only leave the prefix off in the first part of the name. So far we have carbon and we have oxygen. So let's go ahead and write oxygen there. But we can't just name this carbon oxygen. There's one oxygen. So instead of saying oxygen, we're going to say mono, and then we're still going to take the oxy, so monox, but then instead of saying -egen at the end, we're going to end molecular compounds with IDE. So we get carbon monoxide. Let's try Cl2O using the same rules. So I want you guys to try to come up with a name for Cl2O using these prefixes. Let's see what we get. Oh, and I'll give you guys, just because we don't have a periodic table handy, Cl equals chlorine, and O equals oxygen. So treat those as starting points, and let's try to name Cl2O and see what we get. So Stephen, that's going in a good direction to start with. We're going to have two pieces to the name, though. Okay, so Jen's got it there. We're going to start with prefix. We've got to, because the only time we left it off was when there was just one element, or one of the element that we started with, so one of the C's. But down here we have two Cl's. Prefix for two is di. We don't change the ending on the first part of the name, so just dichlorine. And then the second half is going to be a single oxygen, so mono. And we're not going to have monoxide. If we have that double O, it's just going to be mon. And it's not monoxygen. We drop the ending for IDE. So it'd be dichlorine monoxide. Okay, so key to naming these molecular compounds, knowing the prefixes 1 through 10, knowing that you always have to use prefixes unless you have one of the first element that you start with. You name left to right just like you read. Now let's try to go the other way around. I want you guys to try to write a formula for the name. Let's do iodine pentafluoride. So what we just did is we went from name to formula. Let's go the other way around and see if we can go from formula. Oh, I'm sorry. We went from formula to name. Let's see if we can go from name to formula. What's the chemical formula for iodine pentafluoride? And that's right, Tanya. You don't change the name on the first, or change the ending on the first element. So again, the goal here, write out a formula for this name. Okay, Tanya, excellent. Okay, so we're going to have periodic tables handy while we work our way through this. You guys don't want to make up your own element symbols. It would make a whole lot of sense if potassium's element symbol was P, but P is phosphorus, potassium is K. So the element symbols don't always make sense. Fluoride, the element fluorine is F. The element iodine is I. So make sure you look up your element symbols. This is going to be no prefix up here. The only time we could do that is when we just had one of these. So it's just going to be I, fluorine is F, penta, if we go over to our list, penta is 5. So this is going to be IF5. Okay, so just a refresher, this was molecular naming and formulas. For this type of naming, we had molecular compounds made of all nonmetals, upper right side of the periodic table. We're going to move on and do ionic naming. Ionic naming, we had metals or polyatomics. So we started to see elements from the left side of the table. We also saw our list of 10 polyatomics that you guys can find in the Ionic module for my online class, or you can find in the Exam 2 material for those that are here from my seated class. Okay, so Ionic naming and formulas. Let's do 2 of these. Actually, we'll do 3. Okay, so we've got these formulas here. We want to generate some names. Let's start on the left. We name just like we read. Na comes first. You'll have a periodic table with all the names on them to start with, but we got to be able to translate these into names for compounds. Na is sodium. Cl off the table is chlorine. We're going to drop the ene ending, and just like we did for molecular naming, we're going to end in IDE. So this is sodium chloride. If we apply that same logic on the second one, Ca is calcium. We don't change the name on the first part of the name. Don't change the ending. Straight off the table. F is fluorine. And just take note, it's fluorine, not fluorine. The U and the O are interposed. And we're going to drop the ene, end with ide. So a safe bet with ionic naming, you're going to end in IDE, similar to how we did in molecular. Now, just notice something here. Look at this formula. Look at this name. What's missing? If you compare this to what we just did with our molecular naming, what do you guys not see here? So think about that for a minute. Type something out in chat on something that looks like it's missing. Okay, good. So no prefixes. Can't stress that enough. This is one of the most missed problems on the exam, where you try to name something that's an ionic compound and you try to use prefixes. Prefixes are only for molecular naming. So if you see a metal like calcium or sodium that show up on the left side of the table, we don't use prefixes to name their compounds. So last one here. You wouldn't use a di in this name or a tri or anything like that because no prefixes. It's got calcium, that's a metal. It's got nitrate, NO3. This is a polyatomic ion. So all signs point to ionic naming. So we're going to name the first piece calcium. And this is different from the first 2 that we named. The first 2 were straight off the periodic table. This last one involves a polyatomic. We don't change the names of the polyatomics. NO3 is nitrate. So we're done. As long as we know the names of our polyatomics, we just slap the pieces together. Calcium came first, nitrate came second, name is finished. Now this was going from formula to name. Now I want to go over 2 quick examples on going name to formula. We'll do calcium oxide and we'll do aluminum oxide. Okay. I'm going to re-sketch the periodic table here. Okay, this is group 18, group 17, 16, 15. This is group 1 and 2. So those are the ones that we care the most about. If we're going to know how to write ionic formulas, we got to know some typical charges. Group 1 and group 2 are typically +1 and +2. So they follow that nice, neat formula. If we go over to the other side, these were, in group 18, are noble gases. We said noble gases don't play well with others. You could say noble gases don't play with anybody, or they play well with nothing. What's the numeric equivalent of nothing? 0. Noble gases tend to make no charge. And then as you go to your left, group 17 is -1, 16 is -2, 15 is -3. And then we had two oddballs. Aluminum tends to be a +3. Zinc tends to be a +2. So just some good charges to know. Again, this might be something good to put on your note card. Okay, so let's start with this. Calcium shows up in group 2. Oxygen shows up in group 16, if you look at the periodic table. So calcium is going to tend to form, I'm going to make myself a little note here, a +2 just based on where it falls. Oxygen, -2. So we can start to put this together. I can't just slap the element symbols together because in ionic formula we have to make sure they balance out. And hold on, let me check. I've got a question in here. We have 1 minute. Got a question from Margaret, I think. It just says M. The second example has more than one atom. Why isn't it calcium fluorate? Okay, so to address your question really quick before we move on with this, CaF2, we're going to name ionic compounds and end with IDE. The only time that you're going to see something like ate or ite or eum or any weird ending, it's going to involve a polyatomic. So if you want to know what your safe bet is for an ending for an ionic formula, it's going to be "ide." So you don't cover any kind of prefix, no kind of change to the name based on how many we have of each. Because the way we're going to handle that is with charges. The charges are going to take care of telling us how many of each of these we need. Because the goal is to have, if we draw a little line here, these are the cations, they're positive. The right side is the anion. So in ionic compounds, positive half comes first, negative half comes second, and if they're balanced overall, their overall charge should add to 0. So I'm going to take my +2 and my -2, and we can take these numbers, leave the signs, don't really worry about the signs, and just cross them. I'm going to bring this 2 down here. I'm going to bring this 2 down here. So we end up with Ca2O2. Now there's a problem with this. This cross and bring down method works great. So you write the charges of each element above the element, and then you cross the charges down and bring them across. We've got to simplify though. So a 2-to-2 ratio is the exact same as writing a 1-to-1 ratio, just calcium oxide. The +2 here negates the -2 here, they equal out. That's a good formula. If we come over here, aluminum oxide, we've got aluminum being Al, we've got oxygen being O, aluminum is a +3, oxygen -2. We're going to take those charges and bring them down and across. So we end up with Al2O3. And you can't reduce that any further because it's a 2 to 3 ratio. If it was 2 to 4, we could reduce it, but it's 2 to 3. So we're finished. So take just a minute. Do you guys have any questions where this came from? Because we're about to move on. Okay, give you just a minute here. Okay, so I'm going to keep rolling with this. Okay, reaction types. We've got, I'm going to list these for you just so we have them handy. Then we're going to go through and hit all of these we can. We've got combination. We've got combustion. We've got decomposition. We've got single replacement. We've got double replacement. And we've got a number of other reactions. So let's see, we've got hydration, hydrogenation, we've got halogenation, and just for good measure, we've got esterification. Okay, so we're going to do an example of each one of these. Let's look at the top two, combination and decomposition. These are the only two here that are opposite processes. So decomposition is going to break down, and combination is going to build up. So for decomposition, if you look at hydrogen peroxide, these are going to break down into water and oxygen gas. And this happens with light. This is actually a light-sensitive compound. But when it comes to recognizing a decomposition, it's one compound breaking into many compounds. So that one goes to many is the pattern that you're looking for a decomposition. If you think about leaves decomposing in the fall, you start out with a beautiful leaf, and by the time it's done decomposing, you just have a bunch of shreds and pieces that are on the ground. So this decomposition is breaking into a number of smaller pieces. Okay, the opposite of that, if we were to reverse the decomposition of the leaf, we're taking little pieces and building it back up. Or you could think of taking a hamburger and fries and a drink and building a combo, one single unit that's sold. So over here with the combination, we could say we're taking, let's do CO2 plus H2O builds H2CO3. So carbonated water makes carbonic acid. So with this reaction here, we started with this, and you can think of the plus sign in a chemical reaction as the word and. So we have this and this make this new compound that's bigger and more complex. So we're building up. Two things become one. Next up is combustion reactions. Combustion reactions are going to take a fuel, something, let's say CH4, usually a hydrocarbon for our fuel, but it can change. It could be propane, it could be octane, so the identity can change, but tends to be a hydrocarbon. To burn something, you have to have oxygen present, which combustion is really burning. And we're going to make two products. With complete combustion, you make carbon dioxide and you make water. So in recognizing reaction types, we're going to see something, some fuel that we're trying to burn, and then you'll see these three pieces always, plus oxygen gas yields CO2 and H2O. Now, single replacement, if we have, let me think about this, we're going to do Al plus Cu NO3 and because I ran out of room here, I'm just going to make a little arrow going down. So this plus this goes to, and this is not going to be balanced, mind you. It's going to go to Al NO3 plus Cu. So just to balance this really quick, let's say we've got two of those, three coppers, two aluminums. So to recognize this single replacement, I've got the aluminum by itself, and I've got copper paired up. Now, when you look at what happens in the products, the aluminum comes in and it kicks the copper out. The copper goes off by itself. The copper's flying solo at the end of the reaction. The aluminum is flying solo by itself at the start of the reaction. Flying solo, they're single. Now, when you come over to double replacement is more like taking Pb NO3 so my Pb is paired with a nitrate. If we add that to some Ki's, so my K is paired up with my I, in a double replacement, you're going to take the first of each pair and you're going to swap them out. So over here, I'm going to have Pb I2 plus 2 KNO3s. So with this double replacement reaction, the Pb pair started out paired with the nitrate. When I get over here, the Pb ends up paired with the iodide. The potassium started paired with the iodide. When we finish, potassium is paired with the nitrate. So we had a double swap. Nobody ends up by themselves. That's why we don't have a single replacement reaction. Okay, last couple of reactions here. Let's focus on the three H's for the organic reactions: hydrogenation, halogenation, and hydration. Well, each one of these started out with a alkene. So let's say the hydrogenation is going to start with this. So I've got a four-sided ring with a double bond there. We'll start the hydration with the same thing, a four-sided ring with a double carbon bond that's an alkene. And the last one here, halogenation, same thing. So they're all going to start with this double bond present. A hydrogenation, a halogenation, and a hydration are all separated by what comes next. So what we add to this. So I'm going to add an H2O when I hydrate. So for hydration, I'm taking an alkene, a double bond, and I'm adding water to it. When we're finished, that double bond isn't there anymore. Now that's true for all three of the H reactions. So over here, double bond's not there, and we're going to take the water, and we can't split it right down the middle because we can't split that oxygen atom. But what we can do is divide it here, and at both the points, where that double bond used to be, that's where we're going to make additions. So I'm going to add an H to one spot. I'm going to add an OH to the other spot. If you look at a hydrogenation reaction, well, if a hydration added water, a hydrogenation reaction is going to add hydrogen. Same thing happens. I go from having a double bond here to a single bond. I'm going to add to both the spots where I used to have that double bond going across. So I'm going to add right there. Only instead of adding H2O, I'm going to split this H2. I'm going to add half of it here and half of it here. For a halogenation reaction, halogens are group 17 on the periodic table. So F2, Cl2, Br2, and I2. If I added any one of these, I would be doing a halogenation reaction. So I'm going to take that double bond, and let's just do Fs. So I'm going to add F2. Same as the other ones. I get rid of the double bond where the double used to be. By getting rid of the double bond, it makes room so I can add my Fs. I've got an F2 here. I'm going to split it right down the middle. I'm going to add one of them here and one of them there. So all three of these, just looking at general patterns, we've got a double bond here, two lines connecting two carbons. The double bond goes to a single bond. We take what we're adding, we add half of it in each spot. Okay, last one was the esterification reaction. And that's where we had, let's do this. We had a carboxylic acid. This is one of our functional groups. For my online folks, this is from Module 11. For my seated folks, this is from our last exam, Exam 4. So carboxylic acid functional group plus an alcohol is going to make an ester. So we're going to remove water. So I'm going to remove an OH and an H, and I'm going to slide together the pieces that remain. So I'm going to end up with an ester functional group. And every esterification is going to make water. So in looking at an esterification reaction, just for the purpose of recognizing reaction types, I'm going to have a carboxylic acid plus an alcohol makes an ester plus water. And I think we can all agree that the esterification reaction looks way different than anything else that we covered on reaction types. So it definitely stands out. Okay, one sec. And you guys should be able to hear me pretty soon here. Okay, good. All right, so we're going to cover the idea of cis versus trans and functional groups, and we're going to call it a day. Cis versus trans, and again, this is more Okay, so hopefully, can you guys hear me? Should be able to hear me now. Okay, we should be good to go now. We've got one thing left to cover, and that is cis versus trans. This only happens with alkenes, and let's work through one sample on this. Give me just a minute, Stephen. Actually, if you look on a review, you'll have the answer to that question, Stephen. So look on, I'll show you guys before we call it a day. I'll show you where the review is because it gives you a breakdown of all the questions, breakdown by type of question, all that good stuff. Okay, cis versus trans. So to have this, we've got to have doubly bonded carbons, not singly bonded carbons, not triples, but carbons connected by two bonds. So if we look at a skeletal structure, we really have two options here. If I'm looking to see if a double bond is cis or trans, we could see one of these two cases. So let me get a different color marker so this works out a little more cleanly. But we're going to take right along this double bond, if we draw in a dotted line, and I'm going to do the same thing for the one down here. So drawing a dotted line around the double bond. Now if we have groups coming off on opposite sides, opposite sides of this dotted line mean trans. So this is a trans alkene or a trans double bonded carbon because I've got groups coming off on opposite sides, the biggest groups. Down here, I've got a double bond, but my big groups are coming off on the same side. If they're coming off on the same side, it sounds like sim or same, cis. So same is cis, trans is opposite. So going back, if I ask you to identify functional groups, just to wrap up the review, you're going to see something like this, where I'll circle functional groups for you that I want you to identify. So I might circle these two, and we'll have to say, oh, well, that's a phenol, and this one is a thiol. The only way we're going to know that is by knowing our functional groups list. You give me just a minute, I'll pull that up for you guys just so you guys can see what I'm talking about here. And I'm going to share my screen with you. Okay, so we're going to go into my online course here, and we're going to go to our modules. I'm going to go specifically to the organic module, and let's see where I've got it in here. Functional group list. Okay, so right in here, you guys need to know by shape, you need to know the name, you need to know the intermolecular force associated with each of these. So phenols, alcohols, carboxylic acids, amines, and amides, all associated with hydrogen bonding. Ketones, ethers, thiols, esters, and aldehydes, all associated with dipole-dipole. It gives you trends as you go up or down this list. So this is a really rich resource for the organic material to include on your note card. So just make sure you're writing tiny but legibly. Okay. So that's really it for the review. Do you guys have any other questions that I can answer before we call it an evening? Any other questions I can answer for you guys? If not, thank you for coming, and good luck studying. If you guys have any questions, contact me via email, jrwhitehead@waketech.edu. Oh, yeah, Tanya, before I call it quits, I'll pull that up. Okay. All right, I'm going to, yeah, no problem, Jen. Glad you guys could come. I'm going to flip over to screen sharing just to show you guys where the review packet is. Okay, so if you go to, for my online students, exam review materials, scroll all the way down to comprehensive final exam review. It gives you a reminder, please bring a note card. It's got to be handwritten, whatever you can write on one side of your note card. So let's see. Your final exam Chem 90 topics list. Now this is going to bark at me because I have not loaded Microsoft Word on here yet. I'm going to switch over so you guys can see this. Here it is. Okay, so this walks you through all the topics, all the question breakdowns, everything that you need to know about our final. So again, if you have any questions, please feel free to contact me. I'm going to be available before your exam happens. And Rosa, that brings us to an official end of the review. Thank you guys for coming. I'm going to answer a couple questions on here and then call it a night.